The Earth's internal structure. Study of earthquake waves has shown us that the Earth is made up of a series of concentric zones. The crust, mantle, outer core, the different types of shock waves emanating from earthquakes travel through the interior of the Earth, and by measuring these and calculating how long they take to travel, it was possible to work out the depths of the inner layers and infer about their composition. The crust varies greatly in thickness. Beneath the oceans, it is as little as 5 kilometers in places, but extends down to 70 kilometers beneath mountain ranges. Although many kinds of rock are found in the crust, they fall into two main groups. The ocean basins are underlain mainly iron and magnesium, and having densities of between 2.8 and 3.0. In continental areas, granitic rocks predominate. These are rich in silicon and magnesium, and are lighter in both color and weight densities of circa 2.7. The base of the crust is marked by a boundary called the Moho, named after the seismologist Mohorovicic, who discovered it. Beyond the Moho lie the even denser rocks of the mantle, composed of mainly silicate rocks, rich in iron and magnesium. The upper part of the mantle is solid to depths of about 100 kilometers, and collectively, the crust and upper mantle form a relatively rigid shell around the Earth known as the lithosphere. Underneath this exists a partially molten layer that is capable of slow flow. This zone is known as the atmosphere of around 5,000 degrees Celsius. The core is composed of two layers. The inner core is very dense solid iron and nickel, while the outer core is mainly liquid iron, 5,500 degrees Celsius, and is believed to generate the Earth's magnetic field. Crustal movements. Although ideas of continental drift have been around for centuries, the mechanism which moves the Earth's crust was a relatively recent geological discovery of the 20th century. The idea that parts of slow horizontal movement and have caused the continents to change position in relation to each other over long periods of geological time was proposed by Alfred Wegener, a German meteorologist, in 1912. He proposed that all land areas were once part of a supercontinent, he listed evidence which would support his theory that the continents had drifted apart. He pointed to flora and fauna fossils, which only appear in continents that were once joined together, e.g. Mesosaurus, a reptile that lived in Permian times in South Africa and Brazil, and a plant only found in coal deposits of India and Antarctica. Rocks that are identical in structure, composition, and geological sequence in both Brazil and South Africa, as well as rocks in northeast North America and Western Europe. Rocks that in tropical conditions were now found in very different environments, such as coal in the Antarctic and chalk in the British Isles. Other evidence for this continental drift is the coastline fit of North and South America to Africa and Europe. The Mid-Atlantic Ridge was discovered in 1948 by Maurice Ewing, who noted the ocean floor rocks were also younger than had previously been assumed. In 1962, Harry H. Hess confirmed the age of rocks increased with distance from the mid-ocean ridge. In the 1950s, scientists found that iron particles in basaltic lavas extruded along the mid-ocean ridges aligned themselves with the Earth's prevailing magnetic field, and that over the last 76 million years, the magnetic field had switched between the poles around 171 times. The extruded rocks a banding of different polarities reflected on both sides of the mid-ocean ridge. For many years there was considerable opposition to this theory because there was no apparent mechanism to move continents. By the 1960s, discoveries confirmed this idea of moving continents and have led to a body of theory which is known as plate tectonics. Plate tectonics describes and explains the distribution of earthquakes, volcanoes, fold mountains, and the movement of continents. The lithospheric shell around the Earth is broken into several sections that move over the asthenosphere, carrying oceanic and continental crust alike. At the mid-oceanic ridges in the Pacific, Atlantic, and Indian Oceans, new crust is created from the underlying asthenosphere, and in a process called seafloor spreading, the plates migrate slowly away from these central ridges where, as around the edge of the Pacific Ocean, plates move past each other or collide. At many zones of collision, one plate overrides another, the lower plate being reabsorbed into the mantle in a subduction zone. This makes up for the new crust coming out of the ocean ridges, thus maintaining a total material balance over the globe. The radioactive decay in the Earth's core creates movement in the molten rock of the outer core and inner mantle. These huge convection currents in the magma rise toward the surface, pulling continents apart and cause others to collide. Movements of the plates cause pressure and tensions to build up at the Earth's surface, in many cases leading to deformation of the land and the creation of major tectonic landforms. The general term diastrophism is applied to the bending, folding, warping, and fracturing of the crust. The movement of the lithospheric plates forming fold mountain ranges are referred to as orogenic. The creation of complex fold structures, as sometimes involved in orogenesis, is called tectogenesis. There are three types: divergent and transform, or transcurrent. Divergent boundaries are where plates move apart at ocean ridges or continental rifts and are regarded as constructive, producing new crust. Convergent boundaries are where plates are colliding, and either ocean crust is forced beneath continental crust, or ocean crusts form ocean trenches. These are destructive boundaries. Transform boundaries, where plates move against each other, are neither constructive nor destructive. The world's mountain chains have formed as the result of the movement of plates during the geological past, and mark the closure of former oceans or collision of ocean and continental crusts. These major present-day mountain chains are the Alpine Himalayan chain and the Circum-Pacific system comprising the Andes, the Rockies, and the island chains of Japan and the Western Pacific. These mountain chains are comparatively young, having been created in the last 50 million years. They contain intensely crumpled and folded rocks. The transformation of the sediments into mountains seems to have been the result of both compressional force in plates and also isostatic uplift. The intrusion from beneath of large batholiths of igneous rocks is a feature of mountain-building episodes. The introduction of these lighter rocks allows the whole orogenic belt to rise isostatically. However, many of the world's largest mountain ranges exist beneath the sea. The mid-oceanic ridges form distinctive features rising out of the flat ocean basins of the major oceans. The mid-oceanic ridges are where new ocean crust is formed, which is composed of basaltic lava or island arcs, such as the West Indies and in the Western Pacific. Island arcs and the ocean trenches which accompany them are the result of ocean plate collision. The ocean trench is created by the downward plunging of one plate into the mantle, and the island arcs are formed from volcanic activity. Island arcs are formed from volcanic activity in the Benioff zone. Earthquakes are evidence of crustal plate movements. Rocks of the lithosphere deform under enormous pressure which finally ruptures abruptly. The gradual movements in the crust build up until it gives way in one single or a earthquake is a release of stored energy. The point at which the earthquake originates is called the hypocenter, focus, which can be deep within the crust or closer to the surface. Deeper hypocenters produce fewer damaging earthquakes. The epicenter is the point on the surface directly above the hypocenter. Usually, the most damage caused by an earthquake is close to the epicenter. The earthquake generates different types of seismic wave. The faster waves, which can pass through solids and liquids in the mantle, are P, primary waves. The other waves that move through the mantle are S, secondary waves. These are slower and can pass through solids only. Surface waves, Love and Rayleigh waves, are also generated by the earthquake, and these are usually the most destructive to landform development because they can trigger off rapid erosion and deposition. These include large-scale landslides, fault ruptures and mudflows, and some surges in glaciers. They can also cause sudden uplift of areas or a drop of several meters in magnitude. Tsunamis are seismic waves generated by earthquakes and can arrive at coasts with great force, causing considerable damage. They are most common in the Pacific Basin. The 2004 tsunami in the Indian Ocean killed around 230,000 people. The earthquake, which originated, didn't cause much damage, but the tsunami it generated was the worst in the past 100 years. Volcanoes are an opening in the Earth's crust, which results in the outflow of magma, lava, at the surface. The chemical differences in magma produce different types of lava and landforms. Those are located at or near plate margins, with around 75% of all volcanoes situated on the Pacific Ring of Fire.